and thank you all for being here. Hope the traffic wasn't too bad as you came to this meeting. But as an outline, briefly, this presentation will go as follows. First, I will review the purpose of this research, and then go through the analysis methodology and what exactly is being measured. Then I will report on the results for Route 217 and UVX, which will be followed by a summary of the results and a description of the conclusions and recommendations that were made. So the purpose of my research was to optimize existing TSP deployments by adjusting the requesting threshold and evaluating its impact on bus performance and general traffic. Route 217 is a conventional bus route in Salt Lake City that runs along Redwood Road, and this was the primary focus. This research expands on a previous TSP evaluation that compared equipped and non-equipped buses to determine whether TSP in fact made an impact. My analysis focused exclusively on the equipped buses and evaluated the impact that changing the requesting threshold had on bus performance and general traffic. For Route 217, the requesting thresholds evaluated were 5, 3, 2, and 0 minutes, each referencing how late a bus must be before requesting priority. UVX was a secondary focus and is a relatively new bus rapid transit line, BRT line, with dedicated bus lanes for a portion of its route. This is the first evaluation of TSP's impact along the route. Avenue Consultants partnered with us on this research, mostly because they had already developed the methodology to analyze the general traffic for Route 217. And we didn't want to have to reinvent the wheel and do it all over again. But the traffic analysis only applies to Route 217 and was not yet developed for UVX. So for UVX, only bus performance was evaluated. The requesting thresholds analyzed for UVX were off, where no buses requested priority, 5 minutes and 2 minutes, and on, where all buses requested priority regardless of how late they were. For the analysis methodology, several data sets were used. The bus AVL data contain the status of the bus, whether it's on time or late, its scheduled deviation in seconds, and the bus stop data shows where and how often each individual bus stopped to load or unload passengers. The ATSPM data records what happens at each intersection, when the light turns red, yellow, green, when vehicles are detected, and so on. Meanwhile, the DSRC data contain records of BSM, SRM, and SSM messages, the connected vehicle messages that are sent back and forth. The bus AVL dataset was used to evaluate on-time performance, or OTP, which looked at the percentage of time that a bus was considered on time. UTA calls this reliability. I'll reference it as OTP throughout the presentation. The statistical analysis used the bus AVL data and the bus stop data to create a model which analyzed schedule deviation and travel time. Specifically, schedule deviation and travel time were used, were evaluated through the mean, the 95% prediction interval, and the residual standard deviation, which I'll discuss a little bit in more detail later on. The statistical model, the dependent variable, or what was being measured, was schedule deviation and travel time. The independent variable, what was being changed in this research, was the requesting threshold. For explanatory variables, the hour of day and time point and number of stops to load and unload passengers were all included. But not all hours of the day and certainly not all time points were created equal, and bus performance was affected differently depending on them. So these variables were specifically included to overcome the lack of independence that they showed in the data. On the other hand, the number of stops for passengers was included as a covariate to control for the effect that frequent or infrequent stops had on schedule deviation and travel time. The ATSPM and DSRC data were both used in the traffic analysis developed by Avenue Consultants. And this analysis evaluated the frequency at which TSP was served by looking at the percentage of cycles served with TSP and the frequency of TSP served per hour. Split fail was used to measure the impact on general traffic. As a refresher, a split failure occurs if the duration of green does not provide sufficient time to clear the demand that is present. The frequency of how many times or how often split failure occurred in the 10 minutes before TSP was served was compared with the frequency of split failure for the 10 minutes after it was served. If the frequency of split failure increased, then it was concluded that serving TSP did have a negative impact on general traffic. Finally, the traffic analysis also looked at the change in green time to evaluate how the signal timing was changed when TSP was served. All right, so Route 217 on-time performance or reliability is the percentage of on-time departures from time points. UTA defines late as being more than 5 minutes behind schedule. So if a bus were to leave every time point only 3 minutes behind schedule, it would be considered on time and have an OTP of 100%. So this figure shows the results of this analysis and breaks it down by directional peak scenario and then combines them for overall. So first, it's observed that, that for each directional peak scenario and overall, the 0 minute threshold has the highest OTP, with PM northbound being kind of the only exception. It's also apparent that the 5 minute OTP was higher than the 3 minute OTP. But there was then consistent improvement each time the requesting threshold changed from 3 to 2 to 0, with once again PM northbound being the only exception. Now, this was odd because we anticipated as the requesting threshold approached 0 that TSP would be requested and served more often, which would lead to a consistent improvement in bus performance. But going from 5 to 3, we didn't see this. The most likely explanation for this is a change in bus schedule. The 5 minute requesting threshold had a different bus schedule than the time periods when the 3 minute, 2 minute, and 0 minute thresholds were implemented. So overall, when we look at the 3, 2, and 0 minute results, which was when the bus schedule remained constant, we do see an improvement each time as expected. When the requesting threshold changed from 3 to 2, OTP or reliability increased 2%. And from 2 to 0, it increased 2.5%. Now, one of the shortcomings of OTP is that some improvements in bus performance aren't measured. For instance, a bus that's 4 minutes behind schedule and a bus that's 1 minute behind schedule are both considered on time. So if TSP helps a bus get from being 4 minutes behind schedule to only 1 minute, OTP reliability can't measure that improvement. So instead, what we did was looked at schedule deviation. And here we'll show the results of mean schedule deviation. This figure shows that the results of this analysis, and practically the same trends are seen for both OTP and schedule deviation. 0-minute threshold generally has the lowest or best schedule deviation, and that same trend is seen where it gets worse as the requesting threshold changes from 5 to 3, but then improves from 3 to 2 to 0. And again, PM northbound is that only exception. But overall, as the requesting threshold changes from 3 to 2, mean schedule deviation decreases or improves by 15.9 seconds with a p-value of 0.0005. And then that decrease from, as the threshold changes from 2 to 0, is 20.9 seconds with a p-value less than 0.0001. So these low p-values provide convincing evidence that mean schedule deviation improves as the requesting threshold changes from 3 to 2 and again from 2 to 0. Another way to evaluate schedule deviation is through the 95% prediction interval, which is the range that represents the middle 95% of the data. And this range is obtained by determining the 2.5th and 97.5th percentiles for schedule deviation. And then this figure plots these percentiles, the bottom part of the bar and then the top, as well as the median or the 50th percentile value. Now, as the requesting threshold changes from 3 to 2 to 0, several new things are apparent from the results of this analysis. First is that the median schedule deviation decreases, which can easily be seen by this trend line. It decreases 12.5 seconds from 3 to 2 and 25 seconds from 2 to 0. Additionally, the 97.5th percentile values decrease. Now, this is important because it shows that the extremely late buses are helped considerably, even though the median schedule deviation experiences more moderate improvements. There we see decreases of almost 60 seconds, whereas the median is less than 25 or less. And then finally, we see a decrease in the magnitude of the 95th percentile, and shows that consistently drops and gets lower as the requesting threshold changes from 3 to 2 to 0. Now, this 95% prediction interval isn't really a statistical measure in and of itself, but it helps show that the differences in variability as the data, it shows that the variability in the data changes along with the requesting threshold. But to statistically measure the variability in the data, we look at variance. And to measure variance in the data, there were several intermediate steps that needed to take place. First, the residual schedule deviation for each record is calculated, where the residual schedule deviation equals the actual observed schedule deviation minus the estimated median schedule deviation. This was done by direction, by peak, and by time point, as produced by the statistical model. The standard deviation of these residuals is then calculated, which equals the variance. And this graph shows the results of the analysis of the variance. It's interesting to see that overall, the variance decreases with each change in the requesting threshold. So despite the fact that in the previous figures, we saw OTP and schedule deviation get worse as they went from 5 minutes to 3 minutes, and then improve from 3 to 2 to 0. The variance, on the other hand, improves or decreases every single time. Now, this variance metric can be looked at in terms of percent change. Overall, from 5 to 3, the variance changes from 121.4 to 120.5, which is only a 0.7% decrease in variability. Likewise, from 3 to 2 and 2 to 0, we see decreases of 5.9% and 13%. But in total, as the requesting threshold changed from 5 to 0, we see schedule deviation variability drops 18.7%, which is quite a big improvement. Next, we look at the results of the traffic analysis. And 3 graphs are shown here. First, we have the number of TSP served per hour. Then the percentage of TSP served followed by an increase in split fail. And then multiplying these two together gives us the third graph, which shows the frequency at which serving TSP is followed by a negative impact to general traffic. In this first graph, very few buses are more than 5 minutes late, so TSP is not served very often, only about 0.04 times per hour. But this increases as the requesting threshold approaches 0, with TSP granted at most about 1.5 times per hour during the PM peak at the 0-minute threshold. This second graph shows that as the requesting threshold approaches 0, it is less likely that serving TSP will be followed by an increase in split fail. And although this hasn't been verified, this is probably because during the 5-minute threshold, of course, only buses that are 5 minutes behind schedule or more can request TSP. And the assumption is that buses running 5 minutes or more behind schedule are probably dealing with heavy congestion. So even the small changes to the signal timing that happens when TSP is served are enough and have a greater likelihood of resulting in split fail. This third graph indicates that as the requesting threshold approaches 0, the frequency of negative impacts to general traffic when TSP is served increases quite dramatically. But on average, this impact to general traffic only occurs every 241 minutes or every 4 hours. So this negative impact to traffic is still considered to be negligible. When we look at the results of and here's by hour as well. You see big drops or increases in the frequency, but still every 4 hours is not very often. Now, when we look at the traffic analysis at the intersection level, I show 2 different heat maps. On the left, I'll show a heat map generated by column, and on the right, one generated by the table. And this heat map is shown here with the percentiles. So by column helps us see that which intersections are most likely to have these negative impacts to traffic, regardless of the requesting threshold. And we can see that regardless of the requesting threshold, there are certain intersections that have a greater negative impact than the other. The intersection that had the greatest negative impact, you can see, is the PM peak at the 0-minute threshold. It's 70th south every 43 minutes. When the heat map is generated by table, however, you can see it tells a little bit different story. It shows that the greatest impacts are seen in the PM peak, but also primarily at the 0-minute threshold. One of the shortcomings of this is that these percentiles change depending on which column it is and aren't always consistent. So if instead we generate a heat map simply by the number of minutes, where we will see red values if the frequency of negative impacts to traffic is 60 minutes or less. If it's 120 minutes, or about every 2 hours, it'll be yellow. And when negative impacts are every 3 hours or greater, it will be green. And in this graph, or this heat map, we see probably the most relevant results of this traffic analysis, where the vast majority of these cases and these intersections don't see negative impacts. But again, in the 0-minute, we do. In fact, 8 of the top 10, or 8 of the intersections with the greatest frequency occurred in the PM peak at the 0-minute threshold. With 70th South, 78th, 47th, 56th, and 41st South being the top 5. But once again, we consider these negative impacts to traffic to be negligible, and something we hope to discuss at the end is the question, well, how frequent is too frequent? At what point would we consider these negative impacts meaningful? Moving then along to UVX, we look at on-time performance and schedule deviation together. For on-time performance, we interestingly see that same similar trend, how it gets worse, but then gets better. And we're not really sure why that's the case. The schedule for this change day was the same for all the UVX data, so we don't really know why that happened. But as the requesting threshold changed from 5 to 2, we see an increase in OTP reliability of 7.6% and 4.7% as it changes from 2 to on. Again, the same trends are seen for schedule deviation. We see improvements of 24.3 seconds and 15 seconds, each with p-values less than 0.001. Same with Route 217. This shows that with these low p-values, that there is convincing evidence that changing the threshold does, in fact, impact mean schedule deviation and improves it. When we look at the 95% prediction interval for UVX, this graph shows the results of it. And as expected, we see a decrease in that median based on that trend line. However, as the requesting threshold changes from 2 to on, in a sense, the conditions worsen. When we look at the 97.5th percentile value, that upper portion of the bar, it improves from 5 to 2, but then worsens from 2 to on. Also, the magnitude of this interval worsens from 2 to on. So despite having an improvement in the median, in the mean, the variability in schedule deviation from 2 to on gets worse. So to summarize all these results for Route 217, this table shows collectively all those analyses that we just went through. And here, for every single metric that was evaluated, we see improvements. Of course, the negative impacts to general traffic increase, but are still considered negligible. And for UVX, we, for the most part, see positive impacts, but from 2 to on, we do see that in both these instances, for the 97.5th and the magnitude of the prediction interval, conditions worsen. So our overall conclusions and recommendations for Route 217, the data show that as the requesting threshold approaches 0, that OTP reliability improves, that mean schedule deviation and schedule deviation variability improve, and that the negative impacts to general traffic do increase but remain negligible. Our recommendations is that for TSP as implemented, the 0-minute requesting threshold should be used. However, it's advisable that more aggressive TSP settings be implemented, in which case the 2-minute threshold is recommended. Some of these examples of more aggressive TSP settings might be increasing the number of seconds that can be provided to the bus when TSP is requested, or even enabling TSP at intersections where it is not currently enabled. For UVX, the data show that as the requesting threshold approaches 0 or the on scenario, OTP or reliability improves. We also see an improvement in mean schedule deviation, but schedule deviation variability worsens, particularly from 2 to on. So our recommendations are to implement the 2-minute requesting threshold, but to consider utilizing a different TSP strategy, such as phase insertion, or perhaps requesting TSP based on headway adherence, and even developing a bus arrival prediction algorithm. Especially for UVX, that's recommended because these intersections are so closely spaced, particularly on University Avenue in Provo. So, and that limits the benefit that can be received by the buses when granting and being served with TSP. So that concludes the presentation, and thank you.
All right. Well, thank you, Michael, for the presentation. A lot of great information here, and hopefully this has helped to summarize the 300-page report that we sent to you. So now we'd like to get your feedback and questions, and just kind of make sure that, see if there's anything we need to revise before finalizing the report. And so this is where the trick comes in with 21 people. But if you can ask questions or type in questions in the chat box, then we can try and facilitate those. We got a couple of good jobs, so that's good. It's always positive.
Yeah.
Okay, so Blaine says he can ask Michael questions afterward. We are limited in our time, so if anybody, especially anybody from UTA, has got any questions or feedback.
And I can go back to previous slides if that's helpful to asking your question or pointing things out.
Hey, Michael, it's Peter. Can you back up one slide to the recommendations? Talk more about that.
Yeah.
So can you just delve into a little more on your recommendations about the zero versus on Route 217, 0 versus 2 minutes? You say implement more aggressive TSP settings. So are you talking about just refine? I mean, you go from 0 to 2 minutes, but what are you refining with the aggressive settings there?
Right. There are, for example, there are currently several intersections where TSP is not enabled.
Right. Okay. You're like around the freeway interchange.
Right. Typically the biggest intersections that have the heaviest volumes. And I believe that was done initially kind of because people were nervous that even a few seconds of changing the timing could have drastic impacts to traffic. And in every traffic analysis we've done for this, both this one and the original one performed by Avenue, shows that there are negligible impacts to traffic. So by enabling TSP at these intersections where it is not, we could further improve bus performance and theoretically still have very few impacts to traffic.
Right. So meaning we should go ahead and add it to the quote innovative intersections, the CFI, the freeway interchanges. If it works best if we use it everywhere instead of just selective locations on a corridor.
Right.
So that was your conclusion, I guess.
Yeah. And there are so many different dials that can be turned, so many different things that can be looked at. We could also look at increasing the number of seconds that are provided to the bus. Instead of capping it at 10 seconds, maybe we allow 15. Again, it's at those busiest intersections where the fewest amount of time is available for the bus.
Right.
And I think it's important to note too, of course, that we don't know exactly what the impact will be. Those are just things that, we're thinking are possibilities, that was outside the scope of the project, but would be definitely interesting to look at as an option. And we discussed this at some length during one of the TAC meetings, if you remember too.
Yeah, I remember that. So just want to see how it the final product, how you approached it.
And I guess just to kind of, go ahead, Blaine.
So, and you sort of alluded to the fact that we might want to discuss this, but your conclusion is that negative impacts are negligible.
Right.
And I guess it struck me that having a negative impact every 43 minutes at one intersection might not be negligible. Essentially, if the buses are on 15-minute headways, every third bus is causing problems for 10 minutes, right? So I guess I'm just curious how you defined negligible. If negligible means, 43 minutes isn't negligible, but most of the rest of them aren't that bad. Is negligible an hour, 2 hours? How did you define negligible?
Right. And that's an excellent question. And really, there are 10 buses every hour. They run at 15-minute headways, but they're running north and south. So every 43 minutes is really kind of every 8 buses has negative impacts to traffic. But at least for us on our end, and that's kind of why we were hoping to consult with you guys at UDOT more on this, is what is meaningful. Every 43 minutes seemed pretty infrequent, and those negative impacts could just be occurring naturally and may not be a direct result of TSP, but still occurred that often.
And this is David with Avenue. There's an important clarification when it comes to the negative impact. What we were looking is for a negative impact within 10 minutes after it happening. It doesn't mean the impact was for 10 minutes. The impact could have actually been in the first 2 minutes, or because what we were looking at is whether the opposing movements had additional split failures or not. So it could have just had one additional cycle that was a split failure, and we considered that as a negative impact. So it isn't necessarily negatively impacting it for 10 minutes. It could just simply be an extra minute and a half. It could be an extra 2 minutes, whatever a single cycle is. So and we did not, in this research, because it was outside of the scope, we did not quantify that level of data, which would be obviously something that Michael's alluding to, is for further discussion if you wanted to get into more exact details of how those are. But it really boils down to is it really, based on the data, that we really didn't see any significant impacts.
I would add a little bit of context to that as well, that as a former member of our traffic signal timing group myself, when we choose TSP time, I don't think we think about it, but we assume that amount of time is being stolen very frequently. And so once an hour, in my frame of reference, is negligible. So maybe I think I probably helped Michael define that a little bit, instead of us assuming that basically every single bus would be requesting the maximum amount of time. And this, I think, really highlighted for me that we should probably be more generous with our TSP time, as long as there is this lateness threshold, because it's, a couple times an hour isn't nearly as much as every 3 cycles.
Those comments help. Thanks. Go back to slide traffic analysis corridor level. On the TSP served per hour, if there's no lateness threshold, I'm going to assume, and this may be the problem here, I'm going to assume that every bus requests TSP.
Yeah, that's not quite correct. Some buses do leave early, but for the most part on Route 217, that's true.
So if for the most part that's true, shouldn't the red bar PM be 4 times per hour, not 1.45? I mean, if every bus is essentially requesting TSP and there's every 15-minute, they're 15-minute headways, why is that 1.45?
Because it's served, not requested. So a bus may make it through on green and not.
Oh yeah, okay, gotcha. Served, all right. I should have known that.
So if it was TSP requested, it would be at the top, I guess, or B4, but served is based on, whether it needs it or not.
Right. served as whether it gets it.
Gets it, right?
Right. So go back one more slide. So in previous slides where you had these 4 colors of bars, we noticed that the trends were consistent except for northbound PM.
Right?
But in this particular slide, you kind of said, hey, this is really consistent. It's always happening. Yet it strikes me that the trend is not happening in PM southbound or PM northbound. I was a little unclear about your enthusiasm for the consistency in the trend when I thought this was actually less consistent than some of the other trends.
Right. And what I mean by that, if I go back one more slide, or 2 more slides, you'll see that overall, kind of when all the peak data is combined together, overall, we see how it gets worse and then better. And same thing for on-time performance, for reliability. It gets worse and then better overall when we combine all the peak data. But for the variance, when we combine all the peak data, there is still a decrease each time. On average, when we combine everything together, right?
Okay.
Does that make sense a little bit?
It does.
So yes, it's true. There are always exceptions, and here we maybe see that a little more for both PM scenarios, but overall we do see that consistent drop.
I made myself a note that this trend dropping from blue to red was counterintuitive, but I'm trying to think through why I wrote that now.
It's what we expected. We just haven't quantified it yet, per se, especially this variance.
So when you're dropping the threshold, you're requesting and serving TSP more often, and therefore you're improving schedule reliability and therefore variance, essentially.
Right, both of them improve.
Okay. Somebody else have a question before I keep rattling on?
This is Scott Bingham. Just following along with Blaine here. In the AM peaks, we see it's a lot more consistent than the PM peaks. And we talked about that in the TAC committee meetings, where the PM has a lot of buildup of traffic and accidents and events that occur throughout the day. Would your recommendations potentially include maybe TSP being more aggressively served in the morning or the afternoon, or I'm just trying to think through that as how can we create or how can we encourage our PM instances or
Right.
PM to be more consistent and more efficient?
Right. Yeah, and it's a very interesting question. If we have different signal timing plans for AM and PM, should there be different TSP settings for AM and PM to kind of reflect that? Frankly, I haven't thought about that too much. But that sounds like a good idea to maximize the efficiency of the system and improve wherever possible.
So I think if I give the research answer to that question would be, that is a great question, and we should do some more research and see. But it's not as much fun to do that when I can't see everybody's face when I say that.
You didn't see me get my checkbook out when you said that.
I was just envisioning it, Blaine. I was just thinking, oh yeah, that's a great idea. Let's write him some more money.
Let me work on that for you.
Okay, good.
So,
Just to look at that question, Scott, I just went to this graph where we can see kind of that stark difference between AM and PM. I mean, the lowest value for the PM is that 136 seconds, which is about 3 times less frequent than in the PM.
Yeah. Right.
So just make sure that's 136 minutes rather than seconds. So
Oh, pardon me. I'm sorry. Yes.
I don't want somebody to be confused, like, "Whoa, I thought you said that was minutes," but
Thank you. Thank you.
it is minutes. Well, we've got about 7 minutes left here in our allotted time. I guess, I think there's been good discussion, good questions, and Blaine, you may have a few other questions or clarifications. I guess one of my main questions is, are there things that we need to revise in the report to finalize the report, or is everybody comfortable with the report the way it is, the information presented?
While I didn't read all 300 and I believe it's 324 pages. Is that right, Michael?
Unfortunately, yes.
I did get through the first 200 and then 200 and some odd read through the 208, 17, 18, somewhere in there, and perused the last piece. It was a great report. It was a great report. I'm grateful for the work, and I think it's. I'm very excited to share the report when that time is appropriate. So I'm very grateful for it. Thank you.
Thank you.
This is Tom McMahon. There is just one question. It's on the page that you have right there on the Route 217 in your recommendations. I don't quite understand how the second bullet point fits in after reading the first one. Could you run through that again for me?
It's a good.
I had the same question, Don.
When we had met in the TAC meetings and before the analysis was completely finalized and concluded, as a TAC, we said, well, let's do the 2-minute threshold. And as we concluded the analysis and looked at the 0 minute, we really couldn't make a case for why the 0 minute shouldn't be implemented. Yes, we see increases in the frequency of negative impact to traffic, but not enough that it would cause us to recommend not using the 0 minute. So partly kind of respecting the decision that was made by the TAC of favoring the 2-minute threshold, as well as not understanding what the consequences would be if more aggressive TSP settings were implemented. Kind of those two combined were why we came up with that conclusion.
Was part of, I apologize. Was part of the discussion also to make sure that the cycles cleared? We had to have 2 clear cycles in order to allow another TSP through. And if we had one bus that was late, the other one that was on time was granted the TSP, and the other one that was late coming the other direction wasn't able to utilize that TSP. We didn't want those two to conflict.
Right, and for UVX, that's an issue. Route 217, however, does not have that same requirement. So every single bus on Route 217 can get it.
Oh, okay, okay.
But that's partly why we believe we see that how variability worsens for UVX as we go from 2 to on, is because in the on scenario, buses that may be quite early receive TSP and take it from a different bus that may need it more.
Yeah, I think my concern, or I guess my question, ended up being because the statement it is advisable to implement more aggressive TSP, and 2 seems less aggressive than 0. So it was that the relevance between those 2 statements that kind of throws me off.
Right, and that would be because the more aggressive TSP settings that we recommend, such as increasing the number of seconds provided to the bus or enabling TSP at intersections where it's not enabled, those impacts are unknown. So kind of to counteract that, at least initially, is why it's recommended to have aggressive TSP settings, but also then backtrack and use the 2-minute threshold. And maybe that's too conservative. We don't know.
Yeah, and I think as we've kind of talked through this, that a few people have brought up the comments here, and as I've thought through that too, I think what I would recommend we change that recommendation to is that that the 2-minute threshold should be considered with more aggressive TSP settings, because we don't know exactly what the impact is going to be with those more aggressive TSP settings. And like Michael explained, that's not the requesting threshold, but that's the other settings tied to the TSP. And so, we don't necessarily know exactly what would be there.
I was going to say, I think you could define that as maybe controller programming settings or something versus the lateness threshold, which is not directly defined in the controller.
Yep.
All right, any other comments or questions, concerns? David's got my email in there, and you all have my email if you've got any other comments, but we do, I think the last thing I would just throw out there is that we do appreciate everybody's service on the TAC. This project was a much more intensive project than I ever anticipated. And I'm grateful to Michael for all the work that he did. He spent an awful lot of hours trying to figure out what to do with all this data and how to present it. And it took us a little bit longer than we anticipated to get it all together, but I feel like it's a really good product in the end. And he was able to present that in a way that's very understandable, I believe. But we do appreciate everybody's service on the TAC and helping out with the data collection. And, remember back last winter when we were meeting every other week, and we just, everybody put a lot of time and effort into this project. And I do want to thank everyone for that.
Yeah, and from my perspective, this was a very engaged TAC. We did have a huge number of meetings. People were very involved in looking at the data. I think that really helped, even though it probably created a lot more work for Michael and Grant. I was about to suggest that in order to solve this problem of why we dropped from 5 minutes to 3 is because of the schedule change in UTA bus, that we go back and regather that data and look at it again. But Michael lives close to my house, and he could throw a Molotov cocktail through my window. So I thought the TAC was very engaged and asked a lot of tough questions and really contributed to the thinking. And this was really well done. Michael and Grant have really put forth a lot of effort here, so this is good.
Well, from the UTA perspective, I appreciate you allowing us to be part of this. It's been very enlightening for our team as well.
I would agree with that. Thanks, Grant and Michael. Fascinating. I was glad to be part of it. Good job.
Yeah, thank you for all your help.
We all benefited from having the UTA perspective here. It is, after all, your buses.
Welcome
Yeah,
to the commercial
roads.
transit.
Yeah.
Well, if there aren't any other questions or comments, again, thank you, everyone. I don't want to take any more of your time. We've taken a lot of your time over the last year and a half, so we're grateful again for all that you've done. Thank you.
Thank you, everyone, for participating today. I think we'll go ahead and end the meeting. And again, if you have more questions or comments, contact Grant Schultz or Michael or Blaine or others involved on the TAC. I'm sure you know how to contact each other. So thank you all.
Thanks.
Thank you, guys.
Thanks, everybody.